I've written this in two different ways. Let me explain it to you. This over here is an important symbol for you to learn. It is the capital Greek letter sigma, and it means sum of or total. That is just what we've said up here, that we're not worried about just a single force. We're worried about all the forces on the object together. We're worried about the total overall force. So we have to take each force acting on that object and we have to sum it up. That's what this is saying. It's saying, hey, take the total, take the sum of all the forces. So on the left side of this equal sign, we sometimes refer to that as the sum of the forces equals the mass times the acceleration. Now let's look at this. If you increase the left side of this equation and you keep the mass of the object the same, what's going to happen to the resulting acceleration? It's going to go up. That's what we said right here, that the resulting acceleration is directly proportional to the net force. You increase the sum of, or the total forces, you're going to increase the acceleration. Well, what if we keep the force the same and we increase the mass of the object? What's going to happen to the acceleration then? Well, then we have more inertia. We have more of a tendency to resist changes in motion. So the acceleration will go down. If you increase this over here, if you increase the mass, the force is the same, then the acceleration has to go down. So both of these things make sense and is all contained in this equation. Over here, this is another way of saying it. Instead of saying sum of, you can just write the little subscript net, and that tells you the net force. It's very important that you do not ever write this, F equals ma, because that is not true. What is true is that the sum of the forces, or the overall net force, equals the mass of the object times its acceleration. So, make sure that you remember the sigma or the net. Notice too that these equations and this law does not say that a net force has anything to do with velocity. Remember, this is something that Aristotle said, that in order for an object to move at all, in order for it to have velocity at all, there has to be a net force. No. Remember Newton's first law. If an object is moving, it's going to keep moving. If it has a velocity, it does not need a net force to maintain that same velocity. I know that this is strange, and this is where things really get kind of counterintuitive and seem to go counter to our common sense. But I want you to imagine, if you can, our example of that ball rolling on the frictionless table. Let's pretend like the table is infinite, okay? I know this seems silly, but this is how things are in physics a lot. We have to think about silly examples. This ball is moving to the right with some velocity greater than 0. Isaac Newton says, according to his laws, that this ball should do what? It should roll forever. If the surface is frictionless, friction is just a force, kind of a bumping or grinding force that opposes motion due to the interaction of two different surfaces. They're molecules kind of bumping and jostling across each other, slowing each other down, friction. But if this surface is frictionless, then there's nothing at all to stop this ball from rolling. If this ball rolls, it's going to roll forever. The only thing that can change its motion, the only thing that can result in acceleration, is a net force. In order for acceleration to occur, we need a net force, an external force. We need something like friction. We need a wall for it to run into and oppose its motion. We need someone to come along and push it to cause it to accelerate forward. So just because there is velocity, just because an object is moving, does not mean there is a net force. There is only a net force on an object when it experiences a change in motion. When it speeds up or slows down, that is when there is a net force on the object. So if an object is just moving, there is no net force. Another example we are much more familiar with is the example of objects in space. Space is what we call a vacuum. Outer space has no air, no particles to cause friction to oppose motion. So if you're floating in outer space and you throw a ball and it has a velocity, some velocity greater than 0. It's moving this way to the right. Guess what? It's going to move like that forever. It's not going to stop. It's not going to speed up. It's not going to slow down unless it's acted on by a net external force. Yeah, it could get caught up in some planet's gravity, something like that, but otherwise it's just going to keep moving forever and ever. So Aristotle was wrong. Things will just keep moving unless they are exposed to a net external force. The Voyager satellites will move beyond the edge of the solar system into interstellar space, and they'll move forever and ever until they are acted upon by a net external force, some planet's gravity, they hit something, something like that. Things keep moving, and they will not stop moving, they will not change their motion unless there's a net external force. The exact same thing can be said about our example much earlier of the ball that's just resting on a table where the velocity is 0. It has inertia. It's not going to just spontaneously move itself left or right. How do we get it to move? We need a force, a net external force. I have to come along and push it to cause it to accelerate, to have a velocity, to go from 0 velocity to actually rolling. So that requires a net external force as well. Objects will maintain whatever velocity they have, whatever motion they have, whether it's some velocity if they are moving, whether if the velocity is 0. They will maintain that. Newton's first law says they tend to do that unless they're acted on by a net external force. And the larger the force, the larger the acceleration or the resulting change in motion, and the more massive the object, the lower the resulting acceleration or change in motion. And now finally Newton's last law, his third law of motion. Maybe I need to pause real quick and remind you guys what a law is. Remember, a law does not try to explain, it just states how things are related. It shows a relationship that is always true. That's what we're doing. And often it does it mathematically, and that's what we did with the last law. Remember, the second law said that the sum of the forces is equal to mass times acceleration. Okay, so just a reminder, that's what a law does. So the third law, you guys have heard this stated probably as every reaction has an equal and opposite reaction. The third law says that if you have two objects interacting and object A applies a force onto object B, then object B is going to apply a force of equal size back onto object A. If you lean against the wall, you don't fall through the wall. Why not? Because the wall pushes back on you and holds you up. If you punch the wall, quite literally, your hand will hurt and you may break some bones because what does the wall do? It punches you back. If object A applies a force onto object B, then object B will apply a force of equal size back onto object A. Several things that we need to note with this law. This law says that the force that goes back onto the first object, object A, is equal in size but opposite in direction. So here's a very important thing that you may need to know. Forces have direction. They are vectors. They have a measurement, they have a size, and they have a direction. A force can be up, left, right, down at 20 degrees to the surface, blah, blah, blah. They have a direction. And so that's what this is saying, that the force that goes back on object A is in the opposite direction, 180 degrees opposite. Forces are vectors. They have a size and a direction. Let me take a moment here to talk to you about the unit that we use to measure forces. The unit is called the Newton, appropriately named for Sir Isaac Newton. It's abbreviated with a capital N. And let me write this. 1 Newton of force is enough force to cause a 1 kilogram object to accelerate at 1 meter per second squared. Remember the equation, the net force equals mass times acceleration. Well, if your net force is 1 Newton, then that is going to be enough net force to accelerate a 1 kilogram object, that's the mass, and give it an acceleration of 1 meters per second squared. That's the acceleration. If you go back and look at those experiments, that data that we looked at, on the one that had force on the x-axis, it was measured in newtons. So forces are measured in newtons, and forces are vectors. They will always have a size, and they have to have a direction. This is called a force, or sometimes it's known as a free body diagram. These two things are technically different, a force diagram and a free body diagram. For the purposes of this class, we can consider them to be the same. And let's have an example so you guys can know how to do this.